The objective of this framework is to present an open source system on chip SoC ASIC RISC-V design methodology. Included in this video are the RISC-V CPU, the arithmetic floating point unit, and the finite state machine with the VHDL software models. In this segment, I illustrate the chip manufacturing process for the System-on-Chip Core 5 after being sliced from the silicon ingot. Blank wafers are put through 20 to 40 steps to create pattern wafers. These pattern wafers are then tested with a wafer tester, and a map of the good parts are made. Afterwards, the wafers are diced into dies. One wafer produced 20 dies, of which 17 passed testings. The yield of good dies in this case was 17 over 20, which is approximately 85%. These good dies are then bonded into packages and tested one more time. The RISC-V System-on-Chip instruction set architecture is an abstract interface between the hardware and the lowest level software that encompasses all the information necessary to write a machine language program that will run in the system correctly. Above this, machine level is assembly language, a language that humans can read. The assembler translates the languages into the binary numbers that machines can understand. And it extends the instruction set by creating symbolic instructions that aren't in the hardware. So therefore, each category of the RISC-V System-on-Chip instructions is associated with constructs that appear within the programming language. Hardware and software interface within the realms of RISC System-on-Chip Architecture 5. So, many programs have more variables than computers have registers. Therefore, the compiler tries to keep the most frequently used variables in registers and places the rest in memory, using loads and stores to move variables between registers and memory. The process of putting less frequently used variables, which is those needed later, into memory is called spilling registers. The hardware principles related size and speed suggests that memory must be lower than registers since there are fewer registers. That means in this case, data accesses are faster if data are in registers instead of memory. Moreover, data are more useful when in a register, such as in RISC-V SoC. Arithmetic instruction can read two registers, operate on them, and write the result. So the RISC-V SoC system architecture, data transfer, instructions only read one operand or writes one operand without operating on it. So registers take less time to access and have higher throughput than memory, making data and registers both considerably faster to access and simpler to use. Accessing registers also use much less energy than accessing memory. So to achieve the highest performance and conserve energy, an instruction set architecture must have enough registers, and the compiler must use these registers efficiently. In this video, I illustrate the system implementation of the RISC-V system-on-chip subset, showing the major functional units and the major connections between all of these units. All instructions start by using the program counter to supply the instruction address to the instruction memory. After the instruction is fetched, the register operands used by instructions are specified by fields of the instruction. Once the register operands have been fetched, they can be operated to compute a memory address, which is a load or store, to compute an arithmetic result for an integer arithmetic logic instruction, or also equality check for a branch. If the instruction is an arithmetic logic instruction, the result from the arithmetic logic unit, the ALU, must be written to the register. If the operation is a load or store, the arithmetic logic unit result is used as an address to either store a value from the registers or load a value from memory into the registers. The result from the arithmetic logic unit or memory is written back into the register file. And branches require the use of the arithmetic logic unit output to determine the next instruction address, which comes either from the adder, where the program counter and branch offset are summed, or from an adder that increments the current program counter by 4. The thick lines interconnecting the functional units represent buses, which consists of multiple signals. System-on-chip RISC-V ASIC CPU pipelining architecture. Structural hazards usually revolve around the floating point unit, which may not be fully pipelined, while control hazards are usually more of a problem in integer programs, which tend to have higher conditional branch frequencies, as well as less predictable branches. The data hazards can be performed bottlenecks in both integer and floating point programs. Often, it is easier to deal with data hazards in floating point programs because the lower conditional branch frequency and more regular memory access patterns allows the compiler to try to schedule instructions to avoid hazards. So it is more difficult to perform such optimizations in integer programs that have less regular memory access, involving more use of pointers. ASIC system on chip, SoC. I also illustrate in this video the ASIC Universal Verification Methodology Environment, UVM. This segment describes some of the coding guidelines. The system-on-chip ASIC designed software models were written in VHDL. The basic software coding rule is that in order to obtain predictable results, code was kept simple. Therefore, the VHDL software models were generated and written to guarantee that the synthesis would produce the desired result. The objective is to show the artificial intelligence system-on-chip VHDL implementation. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on call operands and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is addition, subtraction, increment, decrement, transfer, logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. The process statement, which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statement inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression and comparison of the value of each of the choices, while the when clause statement corresponds to the matching choice, which will make the statement to be executed. The finite state machine, FSM, is a paradigm mathematical model whose output is dependent not only on the current state of the input, but also on past input and output values. The state machine generated in VHDL, as I have presented in this video, are clocked processes whose outputs are controlled by the value of a state signal. The state signal serves as an internal memory of what happened in the previous iteration. Using the state signal, the finite state machine, the case statement contains a when statement for each of the possible states, causing the program to take different paths for every state. The when statement can also contain code which should be executed while in that particular state. The state will then typically change when a predefined condition is met. UVM is a methodology for building class-based verification environments in System Verilog, taking advantage of object-oriented programming techniques to help with code reuse. So reuse is right at the heart of the UVM environment. The building blocks of a UVM environment are objects, that is, instances of classes as opposed to modules, processes, and functions regarding the Verilog or VHDL. The significance of using objects is that they can be replaced at runtime, given a huge amount of flexibility when it comes to reusing verification components and tests without tampering with the original source code. You can take an existing item of verification intellectual property and replace subcomponents after the sequence of transactions it generates or extends its behavior without touching or copying the source code, and without the original author of the VIP having needed to anticipate any changes. UVM environment recognizes three main types of user-defined object. The three main objects types are the component, the sequence item, the sequence where the corresponding classes are UVM underscore component, UVM underscore sequence underscore item,